This is chapter 6 of Joel Watson's text, Strategy, An Introduction to Game Theory. And this chapter is on dominance and best response. So chapter 6 is on dominance and best response. Let's recall the assumptions we have in place. First is that players commonly know the extensive form of the game. They understand all the possible paths the game could take, and they understand all the possible subsequent outcomes in the game. So they're never surprised by a given path or a given outcome of a game. So we have the extensive form, which is a tree diagram. We also have the normal form, which is a game matrix. The normal form representation captures the idea that players move simultaneously and independently choose strategies. So the normal or game matrix form is better in describing, or it's often better in describing simultaneous move games. The tree diagram is often better in describing sequential move games. And simultaneous move games are obviously imperfectly informed. So when I make a move, if I'm making a move at the same time as you, I don't know what you're going to do, and vice versa. So simultaneous move games are games of imperfect information. Sequential move games may be games of perfect or imperfect information. For example, in chess, it's an open board. You can see what your opponent did before you make a move. So you can observe all of the past moves. But in games like poker, you can't have perfect information, even though there's a sequence of moves, even though it's a sequential game. You don't know the starting hands of your opponents. Therefore, you don't know whether a given opponent is representing the true strength of their hand or they're bluffing. We also assume that players are rational, or they're best responders. They best respond to expectations on what the other player will do. We have some other more minor assumptions, such as perfect recall. We never forget kind of information that was given to us earlier in the game. We'll get to something called complete information, which one result of complete information is that you understand the payoffs for each outcome of the game. And each possible outcome of the game, you understand the associated payoffs. So what do we mean by a dominant strategy? We've gone over it, but we can address the issue a little more formally. Consider two strategies for player I, a player in the game, strategy A and strategy B. So their set of possible strategies, cap S sub I, is, well, A and B. And a set of strategies S not I, cap S not I, for players other than I. So this kind of symbol that looks like a negative I, it means not I in the subscript. We say that A dominates B for player I if the payoff to player I from choosing A while the other players choose a given strategy S sub not I is greater than the payoff to player I from choosing B while the other players choose that same strategy profile, S sub not I. For all S sub I and cap S sub I. That is, the payoff to player I from playing strategy A is greater than that from playing strategy B, regardless of the strategy choices or strategy profile chosen by other players other than I. So if A always leaves you better off than B, regardless of what's played by the other players, then A dominates B. Let's discuss the meaning of dominance a little more. In a normal form representation of a 2x2 game, one strategy is dominant over another for a given player if the first strategy is always a best response. That is, if all best response arrows point to the first strategy for that player. So, and all arrows pointing towards that strategy means that that strategy is a best response regardless of what the other player does. So not all games have dominant strategies, but games that have dominant strategies for all players or for some players are usually easier to solve. Here's a game for which both players have a dominant strategy. It is an advertising game between Coke and Pepsi. Each chooses whether or not to advertise in a market and then takes some payoff. So if they both advertise, they get payoffs of 50. If neither advertises, well, we take it as people still drink Coke and Pepsi at about the same rate, but they've cut their costs. So actually their profits or payoffs go up if they both don't advertise. But in this game, we're going to see that advertise is a dominant strategy for both players. And so we're going to get an equilibrium at advertise. And the paradox of that is that at advertise, each player gets 50, whereas if they could resist advertisement, each would get 55. But the fact that they choose independently and they're each rational best responders actually leads them to that inferior payoff of 50 and 50. Okay, so remember when we're reading this normal form, Coke is the vertical player. Coke can advertise or not advertise. So they're called the row player. They choose which row to put the game in. And Pepsi is the column player. They move horizontally between advertise or don't advertise. And they choose which column to put the game in. So Coke is player one. The player in the left margin is always the first player by convention, and the player up top, the column player, Pepsi in this case, is always the second player. So Coke is thinking about the first payoff, that's their payoff for each outcome, and Pepsi is thinking about the second payoff. We will conduct a best response or best response arrow analysis in the normal form of the advertisement game to show that the payoff to Coke, should Coke advertise and Pepsi advertise, is greater than the payoff to Coke, should Coke choose not advertise or don't advertise, while Pepsi chooses advertise. So that is, that first line says that we're going to show that to Coke, a best response to Pepsi advertising is that Coke advertises. Okay, so see what we did in this best response analysis. We held constant Pepsi's action or Pepsi's strategy at advertise, and given that belief, we asked, well, what's Coke better off doing? Given that fixed belief on what Pepsi will do, we're going to show that Coke is better off advertising, or advertising by Coke is the best response to advertising by Pepsi. But to show that this is actually a dominant strategy for Coke to advertise, we also have to show that the payoff to Coke of advertising, given that Pepsi chooses don't advertise, is greater than the payoff to Coke from not advertising, given that Pepsi chooses don't advertise. Okay, so also we have to show that advertise is a best response by Coke to Pepsi not advertising. So for advertise to be a dominant strategy for Coke, it has to perform better than don't advertise by Coke, whether or not Pepsi advertises or chooses don't advertise. So I would try to look at these two inequalities pretty carefully and think about what they say. Basically what they say is, given a fixed belief on what the other player or players do, a given strategy is a best response if it outperforms any other strategy. Okay? And together these inequalities mean that advertising dominates don't advertise for Coke. we will also show that the payoff to Pepsi from choosing advertise, remember Pepsi's strategy is listed second, so we're allowing that to vary to see what Pepsi is best off doing for fixed belief on what Coke will do, where Coke's strategy is listed first because they're the first player. So we will also show that the payoff to Pepsi from choosing advertise, given that Coke chooses advertise, is greater than the payoff to Pepsi from choosing don't advertise, given that Coke chooses advertise. So advertise by Pepsi then will show as a best response to advertisement by Coke, and will show in the second inequality that the payoff to Pepsi from choosing advertise, given that Coke chooses don't advertise, is greater than the payoff to Pepsi of choosing don't advertise, given that Coke also chooses don't advertise. So that is, that second inequality says that we will show that advertise is a best response to don't advertise for Pepsi. So if Coke chooses don't advertise, Pepsi's best response is to advertise still. So for Coke and Pepsi, if we put all four inequalities together, for Coke and Pepsi, advertise dominates don't advertise because it's the best response to any possible action of the other player. So it is best to choose advertise regardless of the opponent's strategy. We can show that using our best response arrow analysis. And so what this arrow analysis shows is that, well, let's think about Coke first. So Coke is the row player. So they're choosing vertically, thinking about first payoffs for given beliefs on what Pepsi will do, for given beliefs on which column Pepsi will put the game. So if Coke believes that Pepsi will put the game in the advertise column, then Coke can get 50 units of payoff by advertising, or 45 by choosing don't advertise. 50 is greater than 45, so we draw an arrow up in the first column. So this leftmost or first arrow up means that if Coke believes Pepsi will advertise, thus putting the game in the first column, then the best Coke can do is to advertise and get 50 rather than don't advertise and get 45 units of payoff. So that leftmost vertical arrow represents that sort of thinking. Now if Coke believes that Pepsi will choose don't advertise, thus putting the game into the second column, then Coke can get 58 units of payoff by advertising, because they're going to steal some market share from Pepsi. But then Coke can get 55 units of payoff by choosing don't advertise. Okay? So if the game's in the second column because Pepsi chooses don't advertise, or if Coke believes that the game will be put in the second column by Pepsi choosing don't advertise, then Coke can get 58 by advertising or 55 by choosing don't advertise. 58 is greater than 55, so that rightmost arrow up means that a best response to Pepsi not advertising is for Coke to advertise. So those two arrows in unison mean that advertising is a dominant strategy for Coke. Whether Pepsi advertises or doesn't advertise, Coke is better off advertising. Okay, now let's think about Pepsi, the horizontal or column player. So Pepsi thinks horizontally and thinks about second payoffs for given beliefs on what Coke will do. If Pepsi believes that Coke will advertise, thus putting the game into the first row, then Pepsi can get 50 units of payoff by advertising or 45 units of payoff by choosing don't advertise. 50 is greater than 45, so that topmost horizontal arrow left represents the observation that advertise is a best response for Pepsi under the belief that Coke will advertise. Okay, now let's think about if Pepsi believes that Coke will choose don't advertise. If Pepsi believes that Coke will choose don't advertise, thus putting the game into the second row, then Pepsi can get 58 units of payoff by advertising or 55 units of payoff by choosing don't advertise. 58 is greater than 55, so under this belief, Pepsi will choose advertise. And so this observation is represented in that bottommost horizontal arrow left. And that bottommost horizontal arrow left means that if Pepsi thinks that Coke will choose don't advertise, then Pepsi is best off choosing advertise. So if we put all this together, then our strict dominance or Nash equilibrium, our stable point, is a cell where all arrows are moving towards. So that's a stable point in the sense that everyone's playing a best response. And if everyone's playing a best response, then there's no incentive to deviate once you get to that outcome or to that set of strategies. So that point comes at advertise, advertise. That's the Nash equilibrium. An equilibrium is always a statement of strategies. Okay, so the Nash equilibrium is advertise, advertise, and the Nash equilibrium outcome then is a statement of payoffs is 50-50. Coke gets a payoff of 50, Pepsi gets a payoff of 50. This is a prisoner's dilemma or inefficient outcome in the sense that both players would be better off with don't advertise, don't advertise. They would each get 55 because their cost would go down. However, advertise is a dominant strategy for each player. And so you might just ask yourself, without thinking about the best response analysis, well, why don't they just agree to choose don't advertise, don't advertise? So Pepsi and Coke executives go into a meeting. They say, the Coke executives say, well, Pepsi people, will you agree to not advertise? And then the Pepsi people say yes. And then the Pepsi people say, if you agree to not advertise, and then Coke says yes. And so then they walk out of the meeting, and then Coke starts thinking, well, what if Pepsi does advertise? Given that they think we're not going to advertise, their best response is to actually cheat and advertise. And then Pepsi starts thinking the same thing. And then before you know it, this non-binding agreement that they made unravels, and they both end up advertising anyways. So talk is cheap in non-cooperative game theory. And so don't advertise is not a best response for either player. And so it's not what we would call a stable point. We wouldn't predict this as the outcome. Unless they can get something on paper, legally binding, and then we're in the realm of cooperative game theory with this binding agreement. If it's just left to trust, then probably almost every time we try this game as an experiment, we're going to get advertise. So such paradoxes as inefficient outcomes, prisoner's dilemma style outcomes will not always arise by any means in game theory, but often we see these types of outcomes in game theory. So this is totally different than maybe an introductory microeconomics in which you learn, for example, that competitive markets lead to the best outcomes for society. We have whole classes of games in which the equilibrium does not lead to the best outcome for society, and in fact is costly to society or as compared to a more preferable outcome that could be obtained through non-equilibrium behavior. And often we see that it's the job of some regulator or some governmental body to maybe ensure that a mechanism can be designed so that the game is altered and that preferable outcome can be obtained. So a lot of times regulators are changing the nature of the game, the payoffs in the game, through things like fines. And so they're trying to effect a change in equilibrium behavior to get to efficient outcomes for society. But the underlying question is, why do rational players choose inefficient outcomes? That seems like a paradox. Well, the short answer is because they choose independently and strategically. Just like I talked about Coke and Pepsi, maybe they have great intentions, they want to form an agreement, but then they can't trust each other, and in the absence of anything to bind their agreement, then they start thinking, well, I'm exposed to my worst possible outcome if I don't advertise and the other party advertises. And so this lack of trust leads them back to their best response reasoning. And in this case, if they face these payoffs, they would both end up cheating on the agreement and advertising. Let us talk a little more precisely about what an inefficient outcome is. An inefficient outcome occurs if an outcome obtains over another possible outcome that each player prefers. Okay? In the advertising game, each player obtains an equilibrium payoff of 50, but each player's payoff would be 55 if don't advertise were played. But of course, don't advertise is a non-equilibrium strategy profile. Thus, the equilibrium outcome is inefficient. You would like 55, but it's not stable, it's non-equilibrium outcome. So probably if you follow the predictive equilibrium analysis, you get just 50 and 50 to each party. Formally, a strategy profile S is efficient if there is no strategy profile S prime such that the payoff to player I under S prime is at least as good as the payoff to player I under strategy profile S for every player in the game I. And for at least one player in the game J, the payoff to that player under S prime is strictly greater than the payoff to that player under strategy profile S. Okay, so if there is no S prime that meets these characteristics, then S is efficient. Otherwise, if S prime does exist, then S is inefficient. So what are these inequalities saying? Basically, these inequalities are saying for S to be efficient, there shouldn't be another profile that makes at least one of the players better off without making any of the players worse off. Okay? So for S to be efficient, you shouldn't have another profile that could make at least someone better off in the game without making anyone worse off. If there does exist such an S prime that could make at least one of the players better off without making any worse off, okay, that's a free lunch opportunity. And so if there are free lunch opportunities, if you can move from S and make someone better off without making anyone worse off, then we call S inefficient. In the advertising game, let S prime, let the strategy profile S prime be don't advertise. Let the strategy profile S be advertise. And we see that S under this condition, under this definition is inefficient. Because actually both players are worse off under S than they would be under S prime. Both players get a payoff of 50 under S, whereas they would have gotten a payoff of 55 under S prime. A strategy S sub I is a best response to another player's strategy, S sub J, if and only if the payoff to player I from choosing S sub I, given that the other player chose S sub J, is at least as good as the payoff to player I from choosing S sub I prime, given that the other player chose S sub J, but for every S sub I prime in the set of possible strategy choices for player I. In other words, S sub I is the best response if there is no S sub I prime that would leave you better off as player I. We capture the concept of best response within the normal form by drawing best response arrows. A dominant strategy is a best response to any strategy played by the other player. So if your best response is always the same strategy, then that strategy is a dominant strategy. Let us consider a tragedy of the commons game. Tragedy of the commons games are games with inefficient outcomes. So we've kind of specialized in such games so far. We'll branch out a little later and consider many games with efficient outcomes. But as of now, some of the most interesting games have inefficient outcomes because that means there's a role maybe for market intervention or government intervention or some type of policy to make the situation better off. In this game, there are two fisher people. and each is fishing in the same common pool resource, common lake for fishing, but there are only 2 people in this area using the lake. Each fisher person can fish sustainably or choose to overfish. The normal form of this game appears as listed in the game matrix, and so the first payoff is the one in the bottom. Under this notation, the first player's payoff is the one in the bottom left, and the second player's is the one in the top right. So if player 1 fishes sustainably and player 2 fishes sustainably, they each get 4 units of payoff. If player 1 chooses sustainable fishing, player 2 chooses overfishing. Player 1 gets 1 unit of payoff, player 2 gets 5 units of payoff. Okay, and so on. So if player 1 chooses to overfish, player 2 chooses to sustainably fish, then player 1 gets 5 units of payoff, and player 2 gets 1 unit of payoff. And if they both choose to overfish, they each get 2 units of payoff. Okay, we'll justify these payoffs in a following slide, but as of now, that's how you read the game matrix. If both parties choose to fish sustainably, so party 1 chooses S, party 2 chooses S, the lake remains stocked with fish, and they each get a high payoff of 4 units because the fish are reproducing and the stock of fish is growing. And so they'll eat today. Each fisher person will eat today. Each fisher person will still be able to catch fish and eat tomorrow. So this is a relatively high payout. If one party overfishes and the other party fishes sustainably, so you get SO or OS, depending on who is overfishing, the stock of fish becomes somewhat depleted such that the total payoff to both parties, or the aggregate payoff, declines from 8 to 6 units. The party overfishing, however, gets a large payout as he or she is fishing heavily today, but the other fisher person is ensuring that there will be fish remaining in the future. So in that case, the overfisher person is free riding on the restraint of the fisher person who is fishing sustainably. The party fishing sustainably gets a low payoff as he or she is not catching as many fish today and the fish are still being depleted at a slow rate. In this case, the party choosing S gets 1 unit of payoff. The party choosing O gets 5 units. If both parties choose to overfish, so we have OO as the strategy profile, the lake depletes quickly and each party gets only 2 units of payoff. Note that the total payoff in this case decreases in the rate of depletion from 8 to 6 to 4, depending on how much overfishing there is. You know, where most of us have gone fishing, and a big rule in fishing is don't deplete the lake of young fish because they're going to ensure the reproduction and the restocking of the lake. So we usually throw back small, underdeveloped, younger fish. And it's for this reason we don't want to overfish. We don't want to deplete the stock for the next generation. This isn't always the case. I mean, if we're recreationally fishing, we can have this kind of discretion. In cases where somebody is fishing for their livelihood or their survival, it might not be such an easy choice. So there might be an equilibrium in which a lot of young fish are taken. And this might be a role for regulation to try to change that equilibrium, e.g. through fines or some other type of incentive. There are group incentives in this case to fish sustainably. Actions, however, are based upon individual incentives which may or may not be aligned with the group. So what is the outcome or Nash equilibrium of this game? So we're going to conduct Nash equilibrium or best response analysis in this case. A Nash equilibrium is a set of actions or strategy choices that are best responses to one another, or mutual best responses. A best response analysis for each given decision of the other player or for each possible decision of the other player, one can form a best response, and we're trying to identify each of those best responses. So let's conduct best response analysis in this game, and we're going to see this is a game with a dominant strategy for each player. It's what we call a dominance solvable game. Okay, so let's start with player one. And so we're thinking as if we're player one, we're thinking about beliefs about what player two might do. We're thinking about first payoffs, and we're thinking vertically. Okay, because this is the row player. They put the game in either the first or second row. Okay, so if player one believes that player two will choose S, thus putting the game in column 1, then player 1 should choose O because 5 is greater than 4. So if player 1 believes that player 2 will put the game in the first column, then player 1 should choose to overfish because 5 is better than 4. Now if player 1 believes that player 2 will choose O, thus putting the game into the second column, then player 1 should choose O as well because 2 is greater than 1. Okay. So if the game's in the second column, then player 1 can get 2 units of payoff by choosing O, or 1 unit of payoff by choosing S. 2 is greater than 1. Player 1 will choose O. So regardless of player 2's regardless of player 2's strategy, player 1 is better off choosing to overfish. Overfish is a dominant strategy for player 1. Now let's think about player 2, think about second payoffs, and think horizontally. If player 2 believes player 1 will choose S, thus putting the game in the first row, then player 2 will choose O because 5 is greater than 4. If player 2 believes player 1 will choose O, thus putting the game in the second row, then player 2 will choose O because 2 is greater than 1. So again, overfishing is a dominant strategy for player 2. Okay, whatever player 1 does, player 2 is better off choosing to overfish. So the Nash equilibrium for this game, where arrows all move towards that cell, is overfish, overfish. This is not a surprise. Overfish is a dominant strategy for each player, and dominant strategies are no-brainers. It's a no-brainer to play your dominant strategy because whatever the other party does, you're best off playing that strategy. So the Nash equilibrium is the intersection of those no-brainers. Each player chooses to overfish. How do we know that each player or each fisher person overfishes in equilibrium? Well, in the cell OO, all arrows point toward that cell. In other words, OO constitutes a mutually best responsive set of strategies, or a Nash equilibrium. So we can ask if overfishing leads to the best outcome for the fisher people. Is overfishing efficient? And the answer is no, it is inefficient, because there is another set of strategies, sustainably fish, that gives payoffs of 4-4 rather than 2-2. Okay, so if both players could raise their payoff under a different strategy profile, then overfish is inefficient. So this explains again that a Nash equilibrium outcome does not imply a good outcome or a desirable outcome.